All right. So at this point, I would like to do a bit of a poll to see how far along you respectively are. So first of all, I'm going to ask a series of questions representing different levels of progress in the course. Anytime I'm going to pause for 10, 20 seconds and ask you to raise your hand if that's the point where you are. So first, those who are still struggling with the setup environment, with the setup of their development environment, please raise your hand. It's in the reactions at the bottom of the Zoom window. Right, so looks like there are not that many of you. If you encounter any problem where you think I should be able to help, please ask questions in writing. You can also, after I'm done with this part, open your mic and then talk a bit. That's also okay. But not obviously when I'm doing the plenary session. So now people who have done the first steps exercise, the part 3 of the course in the website, can you raise your hands?
Sorry, can you repeat the last question? I'm not sure I responded
So
correctly.
who did the first content part of the first steps part?
You mean all the exercises from 0 to 5?
Like,
or
did you read through it and try the exercises?
completed the exercises or just tried?
Completed or tried it and decided that you didn't want to spend any more time on it, basically.
Okay.
So it looks like we have maybe a third of the room there. Maybe there are more people who raise their hand still. So let me go through it. I think it's already the right time. So first, we need a share for that. So unfortunately, the first chapters of this course are a bit long because I'm introducing all the basic language concepts that we are going to need to do any kind of useful exercise. So I apologize for that. But anyway, we start with the usual hello world. So in Rust, function declarations start with the fn keyword. The main function is called main, as in C and C++. Return types are optional. If you don't specify a return type, it means that you return the empty tuple type, also called the unit type. And in the case of main, it indicates success. And you can print text to the standard output using println, which prints a line of text, not in the printer sense, but in the sense of writing to the standard output. You will notice that this does not look quite like a function call. There's a little exclamation mark here, and we'll get back to this. But first, let's look a bit into variables. In many ways, Rust is a bit of a hybrid between C and C++ on one side and the meta language family like OCaml and Haskell on the other side. The variable syntax is more borrowed from the other side of the generational tree. And so you can do let x equal 4, and this creates a variable called x whose value is 4. This works as in mathematics. So when you create something, you cannot change its value afterward. If you say x is 4 and no, you try to add to x, that's not the mathematical variable anymore. That's more of a procedural language variable. So by default, you can do that. But it's only a mute keyword away to get to the point where you have mutable variables. The idea of having to type one extra word to get mutable variables is that you are encouraged to use immutable variables whenever they fit your needs, because they have lighter syntax, they are faster to type. And this allows you to get code that's easier to read and maintain, because you have less mutation to think about. Once you send that x has a certain value, it will have this value forever. There is, however, one exception which tends to trip up people coming from C and C++, which is that Rust allows for something called variable shadowing. The idea is that if you have a variable named foo, I think to get a larger window, I need to do this as well, right? So if you have a variable called foo, which let's say contains an integer, you are allowed to define another variable also called foo, which contains something completely different, even data of a different type. What this means is that at this point, the original variable named foo cannot be reached anymore. And now you can only access the other variable named foo. You may wonder, why would someone do that? And the main use of this shadowing in Rust is in situations like text parsing, for example, where you have some old value and some new value that's derived from the old value. And the intent is that at the point where the new value exists, people should not be using the old value anymore. And shadowing allows you to do that. Because then you can have the text, unparsed text here, and then you have the parsed text here. And at this point, people don't have access to the unparsed text anymore. I would advise against using shadowing in any other fashion. I personally think it gets confusing quickly. Some people would disagree. And then we get the question of type inference. By the way, I guess the font is large enough now. If not, please point it out. So now that we get variables, one thing you may have noticed is that unlike in C++ or C, I did not need to tell that what is the type of this x and foos that I'm declaring. And that's because Rust uses something called type inference. The idea is that there are 3 scenarios in which the compiler does not need you to tell what is the type of a variable, because it can guess on its own. The first situation is if the thing on the other side of the variable affectation unambiguously tells you what is the type. Like anytime you see a string literal like this in Rust, the type is $str, which reads as reference to string. And therefore, when the compiler sees that you are putting a string literal into S, it knows that S must be a reference to string. The second situation where the compiler is able to infer types is when you are using a variable in a situation where a value of a certain type is expected. In that case, the compiler infers that the variable must be of that type, otherwise your program is incorrect. So for example, Rust has a heap allocated variable size array called vec, which is similar to std vector in C++. And the length of a vec in Rust is of type usize, which is similar to size t in C and C++. It's an integer type that's large enough to hold the size of any variable in memory. What this means is that if you have some integer of unknown type, and now you use it as the length of a vector in a vector declaration, the compiler knows that this integer has to be of type usize because that's needed for this vec declaration to be correct. Finally, numbers are a bit special. I mentioned in my previous presentation that type literals are probably one of the biggest mistakes of C and C++. But if your literals have no type, it means that the compiler needs to somehow guess what the type is. You can tell it by adding a prefix at the end, like for example, this syntax can be used to say, oh, by the way, that 999 is a 16-bit unsigned integer. But if you don't specify it and there is no context anywhere which allows the compiler to guess what kind of number you're dealing with, then there is a default inference rule, which is similar to that of C, which is that integer literals are inferred to be of signed 32-bit integer type. And floating point literal are inferred to be of a double precision floating point type. The reason why we have this fallback rule is to ensure that simple programs will compile without requiring you to annotate everything. Sadly, due to things involving typically generic code, this last rule is not 100% reliable, and sometimes you'll need to spell out the type of your numbers. So now we've covered what gets inferred. Now, what is it that does not get inferred? Typically, type inference problems come from the use of generic types and functions. Let's get back to our vec type. Actually, you do not have a universal vector type that can contain any data as the list in Python. And what you have is a vector of t, where t can be any type. You can have vectors of integers, of floating point, and so on, of structs that you define yourself. And that means that when you write that sort of declaration, of an empty vector declaration, the compiler has no idea what kind of vector you're dealing with. That's a problem, because the properties of the vector type depend on the properties of the content type. So the compiler cannot work with vectors of unknown data because it doesn't know how they should behave. And therefore, in that case, if you need to manipulate empty vectors and you never, ever use them again, like you just declare them, you do not push any data in it and so on, or you push data of also ambiguous type, then you will need to help the compiler. And then you have two ways to do so. Either you give a type to the variable that results from the vector creation, or when you call the constructor of the vector type, you can specify the generic parameters of the vector type using this cute syntax called sometimes the turbofish. Now, if you're coming from another programming language where this is not the usual way to work, where type inference either does not exist or exists but is quite hard to reason about, as with auto in C++, you may be tempted when you start learning Rust to use this everywhere on every variable declaration. I would advise against this for a few reasons. First, Rust type inference is much simpler than C++ type inference. It's much easier to get to the point where you see the code and you intuitively know, oh yeah, that's a vector, or that's something. You do not get, as in C++, these issues where references are implicitly converted to copies of values and so on. And so it's not that much effort actually to get to the point where you get these rules in your head and they make sense. And you will need that as soon as you need to read the code from someone else in the Rust ecosystem, because that's kind of the idiomatic style in Rust to infer everything that can be inferred. And finally, if you get stuck, which is perfectly normal as a beginner, it's actually quite easy to get an IDE plugin like a Rust Analyzer, sorry for that typo, to show you inside of your code editor what the type of your variables are. You can either show them permanently, and then you get the same sort of verbose style that you would have spontaneously written, but it's written for you, including in someone else's code. Or you can have it, and personally I prefer that, when you mouse over some variable, you know, oh yeah, by the way, that's of type this thing. That being said, we cannot just infer everything. Otherwise, this would not be Rust, this would be Haskell or Python. The problem with type inference everywhere is that changing the type of a variable anywhere deep in the implementation of your program can non-locally affect the type of every other variable, function signature in your program and in client code that calls into your program if your program is a library. And this can very easily result in accidental breakages of public APIs. This is why Rust restricts type inference in such a way that you cannot infer types in entities that can appear in public APIs, like function signature, struct declarations, and so on. As a result, you get a limited type inference that's restricted to the body of functions, basically. And that ends up being a pretty good compromise between being concise and being precise. Now let's go back to our printer thing with this exclamation mark. The exclamation mark is here because this is actually not a function. This is a macro. And here you may be a bit surprised. Why do we need a macro just to output some text? And the reason is that this can do a lot more than outputting some text. Like you can just inject variables from the outer scope into your format strings. Or you can do work like printf in C and just put some placeholders and say later on what should be put instead of these placeholders. And you can also name your arguments, like create new names that you use later on. There's a whole mini language inside of println that allows you to generate many strings quite easily. And it's documented here. Like after that, you can annotate your placeholder to say, oh, by the way, I want to print that up to 6 decimal digits and so on. And this is not limited to standard output. You can also have a version that doesn't add a new line, which can be convenient for more complex string formatting. You can also use standard error. You can also write to files. You can also create strings, all with the same mini language. So far, we've been showing examples where println is used with numerical types. What all numerical types have in common is that everyone pretty much agrees how they should be displayed, modulo some options. There's only one obvious way to print an integer to the console. That's not the case if we look, for example, at vectors. You may think that there's an obvious solution, like you put a square bracket and start writing elements one by one and it just works. The problem with that is imagine now that someone accidentally attempts to display a vector that contains 1 billion elements. Now your program will get stuck for minutes trying to print all those elements, spamming the console of the user with huge amounts of textual data that they cannot make sense of. For this reason, some libraries like NumPy and Pandas in Python do some summarized display. They start putting some ellipses in the middle of the display and say, okay, we only show up to 100 elements, and if you want more, you need to ask for it. That's good, but now we need to decide how many elements we show. We need more complex formatting, many language to specify it, and so on. So that's not the direction that Rust wanted to go. Instead, we have two different displays. The display that everyone agrees on for basic types, and the debug display that displays everything always. And if you want any kind of summarized display, then you need to define it yourself. Overall, the consequence of this is that you cannot print a vector because you need to think for a second about what you want to print. Do you really want to send a wall of text to your user if the vector is large? But you can use debug outputs to show your vector when you're doing printf debugging. Some types will implement both the regular display and the debug display. One interesting example of this is the string. Now, as you may know, strings have a bit of a problem from a programming language perspective because you have one double quote character that's used to start them and end them, and you can also have double quotes in the middle. So what do you do? Well, you have to escape them with this slash, and that's where the display and debug implementations of string differ. The display version will show you the string as it's meant to be shown to the user without the escaping, and the debug version will show you the escaping, which then allows you to copy and paste the string and paste it in source code, for example, and it will work right away. So that's all fine and good, but you know, we are developers, we are lazy. So can we get even lazier? Yes, we can. If we are just in the middle of a debugging session where we just want to print random values, we get something even lazier, which is the debug macro. What this does is you give it an expression as a parameter. It prints out where you are in the program, which source file, which line, which column. What is the expression that was passed as input, both unevaluated and then evaluated. Like here, you would get 4 plus 2 is 6. And then at the end of all this, it emits the results. So that means that you can just take any expression in your program and slap a debug on it and get some debug printout. And that's very convenient. Finally, we get assertions. Assertions in Rust.
Sorry. Will the debug be also visible in the release mode or only in the debug build?
Indeed, it will also be visible in release builds.
Okay, thank you.
Debug builds, it's more about having debug info and disabling optimization so that the build is faster.
Get it, thanks.
So finally, we have assertions. So the idea of assertion is the basic version is you give a Boolean expression that should always be true. The program will check at runtime if this expression is indeed true. And if not, it crashes the program because obviously the program is wrong. The main difference that you start with when you go from the C assertions is that Rust assertions are checked even in release builds. The reason for that is that experience shows that if you have expressions that are only checked in debug builds, as in C programs, well, sometimes they end up never checked if people go for release builds right away. That being said, there's a reason why assert is not triggered in debug mode in C, which is performance. And in cases you get such performance problem, then you can use debug assert, which will only do the check in debug builds as in C. In C, failed assertions will abort the current process. There is no cleanup. If you have open files, open network connections, it will all be savagely dropped in a half-written state, possibly corrupting various system resources. That's not always okay. And that's why, by default, in the default configuration, the Rust compiler lets do some cleanup via unwinding and prints a stack trace at the point of assertion failure. It's by default, it's just the point where you failed, but with an environment variable, you can ask for the full stack trace very easily. Finally, this is like print, so you can customize the error message that you get when the assertion is wrong, which can help you produce cleaner error messages, even if that's probably not something you should use for everyday error handling. One last thing about assertions is that often when two things which should be equal are not equal, you want to know what their actual values were. And this you can do with some variants called assert ek and assert not ek, which will show that this unevaluated evaluated to this evaluated to this, and they are not equal. Everything okay so far? Looks like it. Now, can I get a few hands raised for who did the second part of the course? Okay, so about a quarter of the room. Then maybe I can also do this one live. So numbers, after all, that's the heart of numerical computing, right? So let's look into them. We previously mentioned that Rust has some numerical types. It actually has quite a number of them. We have the 8-bit, 16-bit, 32-bit, 64-bit, and 128-bit fixed size, unsigned integer types. So here you can read this as U for unsigned and this for the number of bits of the integer. We get one special unsigned integer type, which is non-portable in terms of size. It's U size. It's of a size suitable for storing the size of any object in memory. This means that if you have a 32-bit computer, U size is 32-bit wide. If you have a 16-bit computer, as in the embedded systems, for example, then U size is 16-bit wide. And if you have a 64-bit computer, like most people, then U size is 64-bit wide. You have signed versions, and you have 32 bits and 64 bits, single precision and double precision floating point types that work like float and double in C++. There are proposals to expand this. I know at least that we now have in nightly versions of the compiler the single precision IEEE 16-bit type, the half precision IEEE type, and the quadruple precision type. But at this point in time, if you don't want to use nightly versions of the compiler, the main way to use these types is via third-party libraries. The literals look much like those of C and C++. One small difference is that you can space out your large numbers to make them more readable, but unlike in C++, this is done with underscores, not single quotes. The main difference, again, is that literals are not typed, which means that you will almost never need typing suffixes to prevent the compiler from truncating your large integers or making sure that you will not do double precision computations when you want to do single precision ones. But the reason why the type inference works so well is it links to a language design trade-off, which is that Rust, unlike C++, does not have implicit conversions. What do I mean by that? So in C++, every time you perform arithmetic or assign values to variable, The compiler will add as many type conversions as needed to get the code to compile. Whether it means taking a narrow integer or floating point type and widening it, or promoting it in programming language jargon, or whether you will take a precise value and truncate bits off in a process known as narrowing. Both of these conversions can be problematic. Narrowing conversions can lose information. By nature, they do. This can result in, this can cause incorrect results. Like, for example, if you have an integer operation that produces a 64-bit result, and then you truncate it to 32-bit, and you used any of the 32 high-order bits, then your result is wrong. Promoting conversions may seem more innocent. After all, you're increasing precision, you're storing more data, so what gives? Here, the problem is efficiency. These conversions may not be free at the hardware level, and the higher precision operations in terms of arithmetic may also be costly. But in a Rust context, we also have a third problem, which is that assuming we had implicit conversions or mixed type arithmetic operators, which has the same effect, we would end up having a type inference of numerical literals failing all the time. Because anytime a number is added to something, the compiler, for example, would have no idea what the type of that number is, because it can work with any number type. Which is why in Rust, you cannot convert types implicitly, and whenever you want to go from one type to another, you have to say so. The easiest way is to do ascast, which work under similar rules as ccast, but with less undefined behavior, and C++ static cast. There are several more advanced mechanisms slowly getting available over time, but they are a bit more complicated and we will not cover them in the course. Arithmetic, again, works much like C and C++. The main differences are that you cannot anymore divide floating points by integers for the reasons stated above. And there is more error checking. The problem with error checking in arithmetic, however, is that arithmetic operations are very fine-grained. And so you can easily get to the point where the error checking has an unacceptable runtime cost. And that's why Rust uses a compromise strategy, where some operations are checked in debug mode, but not in release mode. In release mode, they will silently produce wrong results. It's still better than C and C++ because at least you don't get undefined behavior. Like, for example, casting nan to an integer is stupid, but okay, in the rules of the language. On the other hand, it means that you need to be a bit careful and check your arithmetic using tests and debug builds, because the compiler will not catch the error for you at runtime. Sometimes you do want to have semantics of arithmetic that are not quite like normal mathematics. Like you want to have wrapping addition, saturating addition, and you can have that's implemented as methods of the corresponding integer types. Speaking of which, yes, in Rust, numerical types have methods. You can do things like, you have a pair of floating point variables, you can raise them to integer powers, sum them, compute the square root, all that using methods. People are of various minds about this. For some operations like powers, it works fine, because in mathematics, that's also the way we write the power operator, right? We write the base number and then we write the power next to it on the right-hand side. On the other hand, for other operations like absolute value, square root, those feel a bit weird. Just know that if you can get used to it, it's possible to implement as a library prefix versions of the operators, but the price you will pay is more type inference errors because that's generic code, and generic code and type inference don't like each other. I see that there have been quite a few questions raised. So the font size issue I have resolved. The first, so another question here, maybe I will stop the sharing for now. In exercise 4, shoot, it looks like I swapped the order of parts around, and now I have earlier parts referring to later parts. That's not good, thank you. I will fix it in the text later on. So that's covered, even if I wouldn't call that an answer, unfortunately. So I am indeed suggesting that you only specify types when you have to, or when you are really positively convinced that even a Rust expert would find the code really weird if you didn't write them down. Can you do multi-line string literals? Yes, you can. And you also have, as John pointed out, row strings, which can be used to make things like regexes a bit less painful by suppressing the escaping of things like quotes. How does assert equal work on floating point number? It's exact comparison, which means that it will only work if the number is bitwise equal and is not none. If the two numbers are bitwise equal and not none. In the example that you have posted as a follow-up, Marius, you are summing numbers which do not have an exact IEEE representation, which means that indeed the closest binary floating point number to 0.3 is not perfectly equal to the sum of the closest number to 0.1 and the closest number to 0.2. I would advise in testing code always using some kind of comparison with tolerances, like saying I want these numbers to be equal up to 10 ULPs, or equal within 10 minus 3 relative threshold. And there are libraries for this, even if the standard library doesn't provide it. When to choose usize versus other integer types? Why those array vec dimensions have to be usize? So people who are a bit more familiar with machine integer types will know that some of the integer types of Rust do not have a native implementation at the machine level. Like, it's very likely that your computer does not have built-in instructions for manipulating 128-bit integers. When you use such emulated integer type, you get a performance cost. So that's something you may want to avoid in performance critical code. At the same time, because we have CPUs that have different address space size, we have a 32-bit and 64-bit CPUs, even some 16-bit CPUs in the embedded sector. That means that we cannot just pick an integer type that can hold any size in memory without either going too far and using a type that is not native on the smaller embedded architectures, or going too narrow and using a type that is not large enough to cover the size of any object on a 64-bit HPC architecture. That's why we want to have usize as a compromise for the largest integer type that hardware can efficiently manipulate. Will we have extended precision floating point in Rust? Yeah, as Eric said, I wouldn't bet on it because as far as I know, these days there is only one popular implementation, which is the x87 FPU from Intel. Using this implementation in performance critical code is highly discouraged these days because Intel are not really bothering to improve its execution speed anymore. It's hard for compilers to generate code for it due to the use of a register stack, and it cannot do vectorization as a result. Therefore, my advice is if you would need, for some reason, higher precision than double precision, and you are willing to take some performance hit for that, you should probably rather use quadruple precision or the double, quadruple precision via the emulation provided by GCC's libquadmath. I know it's not super fast, but sometimes you need the precision. I do wish, however, that we will eventually get native quadruple precision in the standard library, if only because we have it in hardware, and it's a bit weird to have hardware support concerns handled by libraries. The compiler should really be taking care of that. Any other question? Then I will leave you work for the remaining 30 minutes of this course. And those who still have environment issues, please again raise them out. You can open your mic and speak up if you want, one by one, obviously, but I can help hopefully. What next? Sorry.
I am the one who has some environment issues.
So which you are? There are several of you, but okay.
So actually, I already have Rust installed and I'm doing the exercises, but when it comes to the downloading of the libraries for especially the image, the converter thing.
So which version of the environment setup do you use? Like the native ones, the container ones, the Devana ones?
Oh, I'm using Windows 10 native.
Native, okay.
Yeah.
And what issue do you get?
It's unable to read my HD.
What kind of error message do you get? You can paste it in the chat, that will be easier.
Okay, sure.
Okay, so basically it doesn't find the HDF5 installation. So I assume you did the vcpkg install AVF5 part, right?
Yeah, and yeah, I already configured your
The
environment
environment
variable.
variable. Did you
Yep.
restart your shell after doing that?
Yes, I did restart. I closed all the PowerShell sessions.
Interesting.
Yeah.
Can you do in the same shell this command?
So it returns all the environment variables, and this is the thing.
So we have the pkg-conf, we have the bin, so that should be in there. And the yeah, and we also need that one, sorry. So next Windows pkg-config, okay. So that's indeed just as it should be. And then the next question is, what's actually inside of these directories?
It's all the DL files and PDB with the HDF file.
Yeah, my question is, are all the things that I would expect to be there actually there?
I kind of assume so, but I'm not actually too sure on what is actually expected, because it's actually my first.
Yeah, that's why I'm asking you if you can just copy paste this into the chat.
Oh, sorry. Oh yeah. Oh yeah. At least. Sorry.
HDF5. So that looks nice. Then I will want this one, obviously, as well. So that also looks cool, interesting. And now for the $1 million question. What is this pkg config file smoking? So yeah, Gregor, that's right that the map command, I think I swapped the order of some chapters at some point, and it resulted in issues later on.
Oh, I see.
So I put it on my to-do list to fix it in a future version of the text.
All right. Okay. Thank you so much.
All right, so now back to this environment debugging. So it's pointing in this location for the include files. Oh, wait. Hmm. So anyway, let's start with that. But so about the questions that were asked. So what next after we work? Well, the thing is at 4:30 we reach the end of the time slot that I've been allocated today. So I could keep people longer if they want to, but I cannot keep everyone because that would be a bit of a lie. You know, we told that this ends at 4:30. So my intent is that tomorrow, I'd like to start with a review of the chapters that a significant share of people have already gone through, as I did earlier. Then we'll go through some more Rust basic, covering more of these chapters over little by little. And around tomorrow afternoon, we'll switch to a more difficult numerical problem, well, a more complex numerical problem called the Gray-Scott reaction-diffusion model. Which will allow us to see some interesting things that happen when we start scaling up Rust to larger problem sizes. I will start by introducing the computation, obviously, and then we will work a bit on the simulation of this computation. On an implementation of this numerical simulation.
Thank you.
As for how many chapters you should complete, so the way this course is written, the idea is that you can work on these chapters whether I'm here or not. If I'm here, you get someone to answer questions, so that's better. But if you see that that's a lot for you to digest and you need a bit more time, you want to go more slowly, that's okay. I will try to explain the concepts if you get lost in later parts of the course because of this. The ideal goal is would be for you to cover the full from lead to dot part by tomorrow, by the second half of tomorrow's session. But if you don't manage, again, don't feel too bad. You can get back to it later on, and yeah. If the later parts feel too fast, I can try to slow down and explain again.
Like kind of forces the 10,000 text, so I'm kind of practicing it multiple times.
What? Sorry?
Zoom like forces like 1,000 characters at a time in the chat, so I am trying to
Sorry, yes. But yeah, in any case, so SDA5 just dumps its includes inside of the directory, but that looks normal, I think. Let me check.
Yeah, just one weird thing I think I should have mentioned previously is
Yeah.
that sometimes it gives me error message they cannot find the GCC, but like few other runs I did previously, it didn't had that error message and it went straight to saying that CTF cannot be found. So I'm not really sure what's the actual issue. Because perhaps it's some
That's a bit weird.
perhaps it's my previous course installation is
It looks like, I mean, to me, it looks like some kind of conflicting environment or something, but everything looks set up just right. So I'm a bit confused right now.
If it's conflicting, then could be because like I think I have last time I tried to install Rust using WASL, both WASL and native. Could be this issue.
So can you say this again more slowly?
Sorry. So I last time tried to install Rust via WASL, and then I also have it on native. So
Okay. And on the WSL side, did it work or? Did it work with WSL or was it also, do you run into different problems?
actually I'm fine now.
I didn't understand that.
I mean like you suggested the possibility of the environment could be conflict, right? And
So
because
it did work on the
yeah,
WSL
sorry.
side?
No, actually I didn't try on the WSL side yet. I
Okay.
was just saying that there's could be another version that could be possibly conflict if I'm not too
I
sure what the
I would be surprised, but maybe. One thing I would try, but that's strange because I didn't get the issue. But there's one issue I got with HWLock, which I didn't get with HDF5. So I'm tempted to try. Is Windows libraries like to name their library with just the name, like HDA5.lib, HDA5.dll. Linux libraries like to name them with lib HDA5, lib HWLock, and so on. I did run into an issue where the pkg config went looking for lib HWLock and didn't find it because the library was called HWLock. I fixed that by copying to lib HWLock. Maybe you can try that with SDF5 and see if it works.
Oh,
Let's try that. That's completely experimental, but who knows? It might work. Ah, interesting. The good old LZF bug. I thought I had fixed that one. So Daniel, which binary are you trying to build here? Oh yeah, the data to pix one.
Um,
I thought I had patched that one to remove that bug. Could I possibly have forgotten to push the patch? Ah, yes. Ah, but no, yeah, for this one I can't. Okay, so we are going to do this a bit differently. So the problem is that I used to, in an earlier version of this course, use LZF for compression of HDF5 files because it's a good compromise for NVMe SSDs. But what happened is that it turns out LZF is actually a bit of a painful dependency, especially on anything other than Linux. And so what I ended up doing in the newer versions of this course was to just disable this feature and stop teaching LZF to people. On the other hand, I cannot I could not easily change that code from the earlier version of the course because at the time I had plenty of code relying on the LZF compression, enabling it, and so on. What I think we can do is for me to push a patched branch of this code, which does not use LZF, like the new versions of the course, and then you can use that. And as a result, you will not get this build error.
Oh, all right. Thank you so much. Thank you so much.
But I will probably not be able to do that in the remaining 5 minutes of this session. So we can maybe talk a bit about this again tomorrow, and in the remainder of this afternoon, I will patch it.
All right. Thank you so much.
So yeah, in any case, we have 5 minutes left. Maybe I can just go through the loops and arrays chapter quickly. And then I'll go it in more slowly tomorrow if that was not clear for everyone. So we've seen basic code constructs. We've seen numbers. The main ingredient that remains for numerical computing is loops. The basic for loop in Rust is quite easy. It's like it looks different, but it works much like Python loops. Like you have this range which is inclusive on the left-hand side and exclusive on the right-hand side. And you can loop over this integer range and print all the integers in the range. And you see that it does not include the last 10. If you are from a different culture where you like to start at 1, well, you will not be able to do so with arrays, but at least you can with integers using this little equal sign to make the right bound inclusive. We have many more range types, not all of which can be used for iteration, but you will see what they are used for later on. Under the hood, the Rust for loops are based on iterators. The basic idea is that when you put something on the right-hand side of the in of a for loop, that thing on the right-hand side will be turned into an iterator, and then the code will repeatedly hold that iterator as long as it returns new values and stop when it stops returning new values. This is a bit similar to the idea of iterators in C++ STL, with one major difference, which is that Rust iterators know where the end of iteration lies. And what this gives us, besides avoidance of undefined behavior, is the ability to modify an iteration after we've started it. Like, we can take this iterator over some integers now, and we can say, okay, no, we only want one value every 10 value. And then we will get iteration 10 by 10. And there are many other adapter methods that you can use that way. Iterate ranges of integers are not the only thing you can iterate over. Two other things you will commonly want to iterate over are arrays and vectors, which work similarly to std array and std vector in C++. So arrays are stack allocated, vectors are heap allocated. Arrays have a size that must be known at compile time. We do not have alloca in Rust yet. Vectors have a size that can be known at runtime. Can have a size that's only known at runtime, sorry. You don't want to manipulate very large arrays because that can overflow your program stack and then your program will crash. And also moving stuff around the stack is a bit expensive when there are many bytes of data to move around. So anytime you start having larger collections of data, you will want to use vectors, not arrays. In general, vectors are more convenient and arrays are more of a performance optimization to avoid allocating in specific cases. You have three ways to create an array. You can just provide a list of elements between square brackets with commas as a separator. You can say that you want many copies of a value, typically 0. Or you can use a function from the standard library that takes as a parameter a mapping from index within the array to value and generates the array accordingly. Vectors support the first two methods via the vec macro, like giving a list and repeating an element. But you don't need the equivalent of array from fn for vec because you have something a lot more powerful, which is that you can take any iterator and just collect it into a vector. This causes type inference problems because you can collect actually in any collection, not just vectors. So you will need to specify the type that you want in one of the two ways I mentioned earlier. And you can also build vectors in the same way that you would in C++ by specifying a capacity and then pushing elements one by one. Both vectors and arrays are iterable, so you can iterate over them instead of iterating over ranges. They can be indexed. Indexes are bound checked. So there is no undefined behavior when you type in the wrong index, you will get a crash at runtime. On the other hand, the check may have a performance cost. To avoid this performance cost, my recommendation would be to use iterators whenever you can, when you need to make operations over arrays or vectors. Rust iterators are quite powerful, so that's not that big of a constraint in practice, and you will see later in this course that this allows us to parallelize much more easily. There is another nice thing in Rust called a slice. The idea is that you can start from an array or a vector and extract a part of it and manipulate it almost like you would be able to manipulate any array or vector. That's a bit similar to the stdpan from C++20, which is no coincidence. And extracting slices manually is basically a more complicated form of indexing. So it has the same problem of indexing. It can crash at runtime and it can be costly due to bound checking. which is why you have slice iterators that allow you to do things, common tasks like slicing your collection into sub-slices of a certain size, or get overlapping windows when you want to do things like stencil problems. So Gregor asks, what's the difference between this array and vector types? So the array is stack allocated, the vector is heap allocated. More precisely, arrays are allocated inline. You can have arrays inside of a heap allocation, but you will not create a new heap allocation every time you create an array in Rust, which is the case when you create a vector. That's the main difference, and then everything else is a consequence of that.
Got it, thanks.
Can we use a concurrently running iterator or generator? So are you talking about parallelism here? Or a different kind of concurrency? Oh, the coroutines.
Coroutines, yeah, coroutine generators.
So that's a strongly desired language feature, which is not quite there yet. It's available in a stable form, but there are quite a few things to fix before it can make it to the stable compiler. And there are some horrible hacks you can use to get it on stable today, but I'm not sure if I would recommend them.
Get it, thanks. But probably it will be ready somewhere like in 2025, 2026, or later.
I don't know. It partly depends on how people will prioritize this development with respect to all the other developments that occur at the same time, how much people will be available, and so on.
Got it, thanks.
And with that, if there are no other questions, I propose that we close it for today.